My name is Jake Schichte, and I'll be covering tubes and the properties of standing waves within them. Let's first discuss the anatomy of a wave. We have two major points of interest. Our first is all points along the center line of the diagram. These are our nodes, a point of high pressure and lowest particle motion. Secondly, we have points furthest from the center line. These are our peaks and troughs, our antinodes. They are a point of lowest pressure and highest particle motion. Next, we will discuss the anatomy of our tubes. There are really only 2 points of interest here as well, the end points of the tube, whether they are open to the surrounding environment or closed off. If the end of the tube is open, then the pressure at that point is equal to the surrounding atmosphere. This is the lowest pressure in our wave, thus the antinode. Conversely, if the end of a tube is closed, the air there is restricted in its movement, the point of lowest particle motion and highest pressure, the node. To demonstrate the properties we'll be discussing, I'll be making a tube out of my hands. By connecting my mouth to my thumbs, I can close that end off to the pressure in my lungs. When I blow, that is a point of high pressure, a node. On the other side, when my hands are closed, it is another point of high pressure, a node, or when I open them, it is a point of low pressure, equal to the atmosphere, an antinode. As you can see, it has a dramatic effect on the frequency. Let's explore why that happens. First, let's discuss how a wave fits inside of a tube. For the main frequency produced by a tube, we denote this order by m equals 1. Now, a closed to closed tube must have 2 nodes on each end. The first and second nodes produced will take the place of these 2 ends. Conversely, in an open-open tube, we have antinode to antinode. Both of these distances represent 1/2 of a full wavelength. However, for a closed to open tube, we have a node to an antinode. This distance is only 1/4 of a wavelength. We will denote the length of the tube by the capital letter L and the wavelength by the Greek letter lambda. We now know that for a open to open or closed to closed tube, our lambda is twice our length. However, for a closed to open tube, our lambda is 4 times the length. Since we know that the frequency is equal to the velocity of the wave divided by its wavelength, we can plug in these values. We now can find that the frequency is equal to the velocity divided by the respective length of the tube. For closed to closed or open to open, twice the length, or for closed to open, 4 times the length. Comparing these 2 states, we can see that a closed to open tube is essentially double a closed to closed tube. Now, if you listen again, you will hear the frequency double when I open my hand. This corresponds to 1 octave change in music. Now discussing the order of the wave produced, which we previously mentioned and denoted as m. While the main frequency will be the widest possible wave to fit in the tube, a tube can support a higher frequency wave as the wave constricts itself to fit within the bounds of the ends. We can thus modify our equation to account for this. The frequency of order m is equal to our previous equation multiplied by m. These equations can come up in a wide variety of circumstances. For example, if you were to make a musical instrument, most famously an organ, which would need a pipe for every single musical note it plays. By rearranging these equations for L, we could solve for the length of every note we want. Or if you were to want to know the resonating frequency of a pipe, as to not contribute to its degradation over time. I hope this was a fun and interesting lesson, and goodbye.